Hello, I hope you're doing fine. So today I'm going to finish the topic of time-independent perturbation theory. Um, I'm going to present an example related to degenerate perturbation theory, which is the Stark effect. And after that, I'm going to make a comment on how this method can be interpreted as an iterative method. So, okay, let me share the screen and let's start. All right. So, okay, we're in the second part of the lecture of this week, where again the goals are to basically study degenerate perturbation theory and then to finalize on the presentation of this time-independent perturbation theory method as being equivalent to an iteration method. So, okay, last time we studied in terms of degenerate perturbation theory, the case of twofold degeneracy, meaning that the degenerate space is of dimension 2. We studied the theory related to the extension of this machinery for a degenerate space of a given dimension. Let's call it n, which can be higher than 2. And well, now I'm going to present another example. So the first example I presented last class was Griffith's problem, 7.9, and this is where we ended. But okay, the new example, which is also part of a Griffith's problem, and it's on the textbook of McIntyre as well, but it's a very important physical phenomena that I think you should know, particularly in this course that we're studying perturbation theory, is the hydrogen atom under the Stark effect. And so this is basically when you apply a constant electric field um, over a hydrogen atom. And so, well, you know your theory of the unperturbed hydrogen atom from your previous quantum mechanics course. And we're just going to perturb it. And of course, this is going to have effect in the energies of the atom by an electric field. And yeah, this is called the Stark effect. Of course, we're assuming that the electric field is constant. It doesn't change in time. And without any perturbation, we have our old friend, which is the basically the Bohr Hamiltonian, where we have the kinetic energy and again potential, which is the atomic potential. So you have the dependence of 1 over r with a minus sign and some constants. And yeah, again, you studied this in your previous quantum mechanics course, and the moral of that story was that you knew that the eigensolutions were identified by quantum numbers, NLM. The N represents the energy, L and M are related to the angular momentum. Basically, so they index the solutions. And well, these are separable solutions that, yeah, usually what you do is to basically propose to solve the problem in terms of separations of variables from which you recover these eigenfunctions. One of them has a radial part identified by the quantum numbers n and l. So this is r, well, capital R of little r. And the other part are basically the spherical harmonics, usually represented with a y. M and L are these angular momentum numbers, and they have a dependence on theta and phi. And again, the energy values, so the eigenvalues of the problem, are identified by a quantum number n, and they depend on this fashion, right? So basically, as minus c squared divided by n squared, and then this is the Rydberg's constant. So these are Rydberg units. So just think of the energy for the case n equal to 1, and then z equal to 1 for the case of the hydrogen atom. The c has been essentially put to give more generality in case you have hydrogenic atoms, which are not exactly hydrogen, but behave like it if you are in the last layers. Anyways, so what this is telling you is that you have degenerate case for the case n greater than 1. So for n equal to 1, actually you have non-degenerate case. But, well, same n, that is not 1, but different L and M have the same energy and therefore are degenerate. So what happens is that for n equal to 1, you can use non-degenerate perturbation theory. But for n greater than 1, you have to use the degenerate one. And now what we have to do is to explain a little bit more in detail our perturbation, right? So, okay, we said we have an external electric field, which is constant in time. And so we're going to assume that this electric field is uniform of a given magnitude E. And if you think about the solutions for the unperturbed hydrogen atom, you use spherical coordinates given the dependence on the potential in terms of R. But, well, at that point, when you don't have a perturbation, you are free to choose the C axis that you want, which is basically related to the polar angle, right? So the polar angle, or the polar axis, actually has some freedom. But in the case of this electric field perturbation, which has a uniform direction, it is actually quite convenient to choose as the polar axis, therefore the z-axis, exactly in the same direction as this external electric field. So for convenience, we're going to choose the spherical coordinate system of the unperturbed problem such that it's aligned with the direction of the perturbative electric field. And in this representation, of course, it is a normal vector C. So this is the magnitude, this is the direction. And the atom being made, say, for a hydrogen atom in the simplest case of a proton and an electron, it behaves as a dipole, right? Okay, the electron and the nucleus, where in the simplest case, of course, the nucleus will be just a proton. You can add more neutrons, but that's out of the question at this moment. And so it will behave as a dipole under the electric field that is perturbing it, right? And you want to know the expression for the perturbation Hamiltonian, which is essentially, well, the potential energy of this dipole under the electric field. So a dipole is defined by the charge times the vector going from the negative to the positive charge. So you have the dipole in this case is, okay, positive charge the electron, or positive charge of equal magnitude as the negative one of the electron, and then times minus the R vector, okay? So R is the location of the electron with respect to the coordinate origin, and we put the coordinate origin located at the nucleus. I mean, at this point, we're not doing like the center of mass correction. You could do that correction. It would just mean to shift the origin and perhaps redefine the mass as the uh, reduced mass, but okay, we're just presenting the generality, and then you can basically define the nitty-gritty details of this calculation. So, okay, the classical potential energy of this is basically minus the dipole times the electric field. If you do that, well, there's a minus sign that cancels this one. So you have E times the R vector times the electric field, which is the magnitude times the direction. And you notice at this point that essentially R dot C hat is just going to give you the C component by the way you chose your coordinate system, right? So, I mean, this is the classical expression. The quantum version, if you are in the position representation, is going to have the same expression. So, okay, the quantum version of this potential, it's basically the operator equivalent, but in the position representation, we just have the same. And so if you define H prime as the related operator in position space or position representation, you have, okay, electron charge, or proton charge, sorry, times the magnitude of the electric field, and then C dot R, right? Which is basically this formula I just organized in a different way. So which is the same result, big E for the electric field times C. And then this is just the spherical coordinate representation, where C is equal to R cosine of the polar angle. So far, so good. You're familiar with these coordinate systems, and we have expressed it. Now we know the Hamiltonian perturbation, right? And so we want to calculate the corrections. So we first tackle the case n equal to 1, which we know is not degenerate. And we can use non-degenerate perturbation theory, right? So the first order correction, and of course the unperturbed states are what we found for the unperturbed hydrogen atom with these quantum numbers identified. Notice the subscript 0 is indicating that it is unperturbed. So, okay, first order correction, perturbative Hamiltonian uh, over the unperturbed states. We're going to do as an example the ground energy case. So, again, that is the case identified with n equal to 1, which basically it only has a single eigenstate, which has quantum numbers L equal to 0 and m equal to 0. So we're using this notation. And the average value of h prime under this state, well, you have to plug in the formula for the Hamiltonian, which is over here. So you have an EE outside, and then the average of C under this ground state. And well, okay, let's present the calculation and then I'll make some comments related to it. So, okay, basically, if you were to plug in, you'll have the C operator, which is our cosine of theta in the spherical coordinate representation. You have the Jacobian of related to the integral that you're performing, and then psi conjugate to give you this one for the ground state, right? So, okay, you could plug in the values, of course. Actually, what will happen is essentially, okay, you can do the substitution, which is fine with the formula for the wave function in the ground state. But you'll notice that this is 0. And essentially, it is 0 because, okay, you'll have r cubed, then times the r, but then you have cosine of theta, sine of theta. And so the thing is that cosine of theta, sine theta has an odd symmetry over the integration interval that we have minus pi and pi for the polar angle. So this vanishes due to the odd symmetry of the integrand. When you substitute the formula, you get to this conclusion, but basically using Fubini's theorem and separating over each variable of integration and just considering this case. However, it actually could be anticipated a little bit beforehand. Um, well, because essentially you'll have the C operator, which is coming from C hat dot R vector. And you can think about the fact that this expression or this Hamiltonian H prime is odd with respect to R. So just think about that for a second. I mean, of course, the fine detail calculation is over here, but think about it. In any case, what this is telling you is that the first order correction to the energy of the ground state is 0. So there is no first order correction for the ground state of hydrogen. And so at that point, we cannot predict the so-called start effect at first order. And again, this is something that I want to iterate because I want to enforce this fact of noticing the symmetries of the Hamiltonian, etc. So again, the Stark potential has such symmetry with respect to R. Look at this formula. This is exactly where you're looking at it because the electric field, which is EC, is fixed. So if you apply the Pareto operator, which is basically operating solely on R, uh, well, it will flip it, right? So it will get a minus sign. And so the Pareto operator applied to H prime gives you minus H prime. So you have to notice that it has quite a lot of relation about this, because if you plug in this formula, you might notice that basically you are integrating an odd function, c dot r, over even states. Well, once especially you do the multiplication that gives you this, right? So this would be even. So think about it for a second. I mean, in any case, a calculation is justified by this and noticing the odd symmetry of this function. Um, So let's go to the next case, which is the excited states, which we know are degenerate. So they are going to need degenerate time independent perturbation theory. And for n equal to 2, you have basically 2 squared for degeneracy. And in general, if you remember your course of quantum mechanics of last semester, well, states of hydrogen that basically are related to the nth energy level are n squared degenerate. So for 2, you have 2 squared, of course. For the case 1, it's not degenerate because it's dimension 1. So yeah, again, the degeneracy of the eigenspace corresponding to the nth energy is n squared for the hydrogen atom. So this is just what we're using. And we know that we have 4 states. That's actually coming from something that you know, which is how many states are available, which are numbered by these quantum numbers uh, L and M for a given n. So, well, a 2s state means that you have L equal to 0, and P state means that you have L equal to 1. So for that, you have the option when L is equal to 1, which is the case of the P state, you'll have basically minus 1, 0, and 1. So, well, in these cases, L is equal to 0 for the 2s states, and so M has to be 0. So again, we're just trying to fix ideas, and remember that in degenerate perturbation theory, the mantra is to diagonalize the perturbation Hamiltonian in the degenerate subspace. Now, what is the degenerate subspace, right? And that is what we're trying to say. So it has dimension 4. So we try to propose a basis in terms of the all the unperturbed states that are um, well in this degenerate subspace, and they are of this form. So again, n is equal to 2, so that is fixed. And then you have the freedom for L and M, where L can either be 0 or 1, and M basically goes from minus L to L, right? So for L equal to 0, M only has the choice to be 0, which is related to the 2s state 2, 0, 0. And for L equal to 1, which is P state, M has or can go between minus 1, 0, and 1. So that's why, okay, you have the quantum number n, you have the quantum number L, which is equal to 1 in the second case, and then you have the option of M minus 1, 0, and 1. So this completes our 4-dimensional basis, sorry, of the degenerate subspace associated to n equal to 2. So in principle, we have 4 basis elements, right? So what we want is to calculate or diagonalize a matrix in this degenerate subspace. And therefore, the matrix in general will have 4 squared, meaning 16 elements, right? Because you have to calculate these products of sandwiching the C operator with any 2 states belonging to this set, and then multiply by um, proton charge times electric field magnitude. However, we're going to try to present some arguments in order to show that many of these elements are 0. And so there are many ways to do it, of course. One possible way would be to analyze that, well, precisely our Hamiltonian perturbation is related to, or has a symmetry related to the parity operator. So that's one avenue. I'm not going to do it like that in this case because I want to present a subtopic while I work on this exercise. The second option, of course, is to simply, you know, um, calculate all the elements and then give arguments on why some of them vanish, which is actually the approach that McIntyre follows. And so actually, if you notice, McIntyre doesn't present the theorem that we showed last time regarding like finding an operator that commutes with the unperturbed Hamiltonian and the perturbation, etc. But if you look at the way he does this problem, he in principle presents the 4 squared matrix to be calculated, and then he gives arguments that rely very close to parity and symmetries of that kind in order to say why they vanish. So although he's not saying that he's using the theorem, he's definitely exploiting the symmetry for this particular problem where perturbation potential is all under the parity operator to banish it. So you could say that under the sheets, he's doing that approach. Um, I'm gonna do it a little bit different using some rules that actually are coming from the fact of exploiting symmetries like parity. And so these are called selection rules. Okay, and the reason I'm doing it is because actually this Stark effect problem for the hydrogen atom is a textbook problem in Griffiths that is given to be solved by the students. And so this is a hint. So I wanted to use it to illustrate how the problem could be performed in this fashion. And these selection rules, which actually belong to a previous chapter in Griffiths, you may or may not have seen this in your previous course. But essentially, these are rules related to the matrix elements of a vector operator. So it doesn't need to be an angular momentum exactly. It can even be the position operator or a component of the position operator, but it's just a vector operator, okay? So the matrix elements of a vector operator component will only be non-zero. So notice that I'm emphasizing that this is a component of the vector operator. I haven't said which component, but we know that it's a component of a vector operator. So the matrix elements of a vector operator component will only be non-zero if this condition holds, which means that L prime minus L is either 0 or plus minus 1, where L prime and L are basically the angular momentum numbers for the two states that I'm considering. So that is the case in our problem because essentially we have no other choice, right? I mean, L and L prime are either 0 or 1, so the difference is either 0 or plus minus 1. So we are in those grounds. And M prime minus M, which is the second condition, has to be either 0 or plus minus 1. Okay, so this is the first rule that is eliminating transitions related to this matrix because we couldn't go from 1 to minus 1 because then the jump would be of size 2. And here we only can have jumps of basically size or step 1 or step 0. So these transitions vanish and we don't need to calculate them, okay? Um, so now I'm going to be more specific and not talk about just abstractly of a given vector component or vector operator component, but concretely for the C component, okay, which is actually the problem we're dealing with because it's proportional. So 2L prime and prime, uh, then sandwiching C, sandwich 2LM. So the rule for the C component is that this is equal to 0 unless the following happens, that M prime should be equal to M. So we can have two cases, right? Either M is equal to 0, or actually three cases. M equal to 0, M equal to 1, M equal to minus 1, and M prime equal to M in these three cases. So, okay, we have this stronger rule. So this is telling you to choose matrix elements with the same M to prevent the vanishing of the matrix element. And the last rule, which is actually quite helpful, so which is called Laporte's rule, is that 2L prime and prime, sandwiching C, sandwiching, well, operating over 2LM, is equal to 0 if L prime is even. So that means that if you have L equal to L prime, this is going to vanish, because then, of course, you'll have an even number, 2L, so that would be 0. And I mean, notice that for L, we only have the possible choices 0 and 1, right? So they can only be different, and this means that one of them has to be 0 and the other has to be 1. And when you have L equal to 0, that automatically is telling you that M should be 0 because this is related to the to S state. And yeah, I mean, L prime has to be 1 in this other case, and we know that M prime has to be equal to M from these rules. So sometimes in a quantum mechanics course where you study the hydrogen atom and angular momentum, this is studied. If you haven't, I would ask you to please just briefly read this section. I mean, to get you familiar with what I'm saying. So I'm taking these properties for granted. I'm using this knowledge. Uh, Essentially because I want to present the selection rules. And in fact, they will appear again when we study time-dependent perturbation theory, where the electric field will be time-dependent. So I just want to introduce it, right? Again, there are three avenues. Either compute the 16 matrix elements by brute force, which would take a lot of time. Second, use the theorem that we saw last time, where we want to find an operator that has some commutation with H and H prime, which in this case, the form of the Stark potential, which has this C dot R or hat C dot R, is telling you that probably the parity operator would be a good choice for that. In fact, again, as I mentioned, what McIntyre does is to, in principle, pose the matrix with 16 elements and then give parity arguments to show why most of them vanish without actually invoking a theorem. So the procedure is equivalent in that way. In this case, I'm using some rules which are derived actually from properties or symmetry properties like the parity operator, particularly for vector operators. So that's why we're getting this. Okay. But in any case, I just want to present it and use the hint on Griffith's problem. So you can see how this is performed. And so again, where were we? Oh yeah. So basically, we can only have the case L equal to, or sorry, R not equal to R prime, and M equal to 0. So M prime has to be equal to 0 as well. So L and L prime have to be different, meaning that, okay, for fixed N equal to 2, then one of them has to be 0, and the other has to be equal to 1, right? So which is where R. Then M has to be 0 for L equal to 0. So we're in this case, and M prime has to be equal to M. So from all possible choices in this case, for M, which would be minus 1, 0, and 1, the only one that is going to give us a non-zero element is going to be the case M prime equal to 0. So that's why the only matrix element that we have to compute is this one and its conjugate, right? Okay, because we could have the other case, 2, 0, 0 in this side of the inner product and 2, 1, 0 on this side. But that is just a conjugate because the matrix is Hermitian, and we already know that story. So if we calculate this one, we're done as we only have to conjugate um, to get the second element. And yeah, again, I really encourage you to read McIntyre's because I really like the fact that in a way he's not using the theorem, but he's presenting the arguments of the operator with a given symmetry in order to banish many of the integrals in this particular case. However, of course, you can check that on the textbook because that example is already worked out. I wanted to do something that in principle is not appearing in the textbook, like basically solving the problem that Griffiths is indicating you to do. And the way McIntyre is doing it, just that you're clear if you read that section, is in terms of parity and dependence on the azimuthal angle. So check it out. In any case, when we perform that integral that we care about, we have this, right? So this would mean that you have to plug in basically your um, eigenstates of the hydrogen atom with the quantum numbers 200 to 10. We already know how H prime combined with the Jacobian looks in the spherical coordinate space, because we would have r cosine theta multiplying basically r sine of theta, blah, 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 the remaining. So that's why you get the r cubed cosine theta, sine theta, plus, of course, the differential elements. So you have to plug in your decomposition in separation of variables, where you have a function of r, the spherical harmonic for the state to 0, 0. Likewise for 2, 1, 0, the radial part and the spherical harmonic part, identified with appropriate quantum numbers. And you can separate this integral, so one part for the radial functions, the other for the spherical harmonics. Um, then, of course, if you were to plug in the formulas for R2 0 and R2 1, you can also look at the formulas of McIntyre if you don't remember them. You would get this. So you have the Gaussian part, and then R to the fourth combined with the R cubed, and then 1 minus R over A naught, where A naught is related to, of course, the Bohr radius, etc. And if you plug in the spherical harmonic section on this part and you further separate, you'll have cosine squared of theta, sine theta d theta, and then, of course, the azimuthal integral, where it has no uh, complicated function. So that one you can do easily. In fact, this one comes easily out too because, well, you have sine of theta, which is the derivative of the cosine, and then, okay, this function, you're integrating over 0 to pi. So, well, basically you can use calculus and just compute this one. And the remaining part is just the radial one. So basically you have the difference of two integrals. One is basically an exponential times r to the fourth, and the other is proportional to an exponential times r to the to the fifth power. So, I mean, in principle, the way you would solve this would be by integrating by parts and reducing the order of r until you get to exponentials that you can solve. Uh, we're just going to assume that we know how to do this procedure. If you want, use a table of integrals or a numerical solver for this. Um, but if you compute this integral and then you balance against the other terms, you have minus 3 charge of the proton, electric field, and A naught, which is related to the Bohr atom radius. Okay, we know the two terms that are non-vanishing. Notice that in the basis that we're using, we gave a given order, right? So we started with 2, 0, 0, then we went to 2, 1, 0. So these two are the matrix elements that we are involving in this calculation. And the two others basically are not appearing, right? So what we have in the matrix representation under this basis in this order, of course, so keep track of the order, of course, that's important. Well, yeah, right. So you have the mixed elements. Actually, this is a real number, so the conjugate is itself. So that's why you have in the off-diagonal terms this element, minus 3 e capital E A naught in the off-diagonal, 0 over here. And for the others, all the elements are 0. So again, keep in mind the order of the basis, but these are the only non-zero elements of the Hamiltonian perturbation matrix using this basis representation. Now, well, we know that we have to diagonalize the matrix of the perturbation in the degenerate space, but before that, we have to know the, well, eigenvectors in order to do that, and that means to also calculate the eigenvalues by means of a characteristic polynomial. So we know that because we'll have a singular matrix when we want to calculate the eigenvalues, this matrix H prime minus lambda I, so I is the identity matrix, lambda will be the eigenvalues of the matrix that we want to calculate, so of course it has to be 0, and therefore it's determinant because it's a singular matrix. So this comes actually pretty neatly because, well, think about it, right? I mean, this part is going to be completely diagonal. So this is accounting for the lambda squared part because you would have minus lambda when you subtract the minus lambda identity. And the other part, basically, if you use properties of determinants, so this part is calculated quickly. And in this other part, you'll basically have lambda squared minus 3 EEA naught squared. So this is why the other part is appearing. So you're kind of like decomposing this in this part, which is quite easy, and then a 2 by 2 matrix for which the characteristic polynomial is simple to see or to foresee in terms of the formulas for 2 by 2. And so this polynomial of fourth order in lambda has to be 0, where lambda are the eigenvalues. And the solutions are quite evident in the sense that, well, this means that either lambda is equal to 0 or lambda is plus minus this value. And so this actually gives a nice interpretation or a nice understanding of what's happening because Uh, well, what are the lambda equal to 0 eigenvalues? What are they related to? Well, clearly they are related to these two elements, where if you look at the matrix H prime, basically the effect of the Hamiltonian perturbation over the last two vectors in the basis is nothing, right? So they give you the 0. So that's why the lambda 0 eigenvalues are appearing. And they're related to these two vectors with m equal plus minus 1 and with L equal to 1. So uh, this in principle is kind of telling you that you could think of, because we know the effect of this over these vectors when you apply h prime is 0, you can try to diagonalize this 2 by 2 smaller matrix. So that's simpler to do. And you're familiar with those combinations by means of entangled states, or the ones that are linear combinations of plus minus the vectors. But in any case, I will just explain in detail. So if you take the difference of 2, 0, 0 with 2, 1, 0, and then of course you normalize, uh, by the combination that you do in terms of the columns and rows, etc., actually you'll notice that the eigenvalue that you get is lambda plus. So this is the eigenvector. I mean, this is equivalent to basically having found the eigenvalues of plus minus this. To plug in the equation to find eigenvectors is going to be restricted to these two. And with this system of equations, you'll know that basically the coefficient for this one is the negative of this other one. And then this comes from normalization condition. So in your mind, think how we're doing this problem. For the other eigenvalue, which is the minus this, well, this actually corresponds to adding just these two. So, and normalizing, of course. In fact, well, since we have found the eigenvalues and the eigenvectors, um, these eigenvectors are quite helpful because they will let us diagonalize the perturbation matrix. So these are the so-called good states that we were looking for. And the lambda plus minus in this case, of course, instead of the lambda 0, are basically the first order corrections to the energies in the degenerate case. So again, so you have this, right, plus minus. And I didn't add a subscript here of plus minus because here's the case 0. And so this eigenvalue actually appears with multiplicity too. But in any case, what I'm trying to say is that instead of choosing this basis for the first two, I replace these two with the plus and the minus part. So where you subtract and you add them with these combinations that we know that they produce, well, for this one, this is an eigenvector with eigenvalue lambda plus. This one is an eigenvector with eigenvalue lambda minus. The matrix will look diagonal under this basis representation, right? And okay, this is clear because of course I'm using the eigenvectors. This is the eigenvector corresponding to the lambda plus. This is the eigenvector corresponding to the lambda minus. So when you apply the matrix to the well, to the eigenvector, it will produce these ones. And in this basis, of course, these are in principle eigenvectors, but with eigenvalue 0. So we have diagonalized the matrix at this point. One important thing to mention, okay, so we have what we were looking for, which is to diagonalize the perturbation matrix in the degenerate subspace, so under this basis representation. But you notice, this is important to notice, that the perturbation has lifted the energy degeneracy only partially. In fact, only for these two states or their equivalent, right? These two, because this subspace, which is related to m equal to 1 and m equal minus 1 with L equal to 1 for n equal to 2, is still degenerate. Why? Well, because the correction to first order provided by H prime for these states is 0. That's why we got the eigenvalue 0. So the first order corrections to the energy for these two states is 0, which means that the degeneracy is not lifted. So they are still degenerate. There should be another method to to leave the degeneracy, not to first order for these two. But for the other two, I mean, we have lifted the degeneracy, we have found the eigenvectors, we have diagonalized the matrix, and our job is done for the moment. So again, I wanted to expose you to the selection rules, which are related to vector operators, components, and operators symmetric, or their symmetries, sometimes related to parity. Again, I state that there are three equivalent ways to do the argument. One by the theorem, where you find an operator commuting, which I would suggest to check on the parity. Then check on the Griffith, the McIntyre way of doing the problem, which is giving arguments on why the elements vanish. He proposes the full matrix. He simply then indicates why many of the elements vanish. And he's not using the theorem, but he's using parity. So under the curtains, there's some use of these symmetry operators in a way. And then, yeah, I mean, Griffith's problem is just indicated to be done, or this is the hint given to use the selection rule. So that's why I wanted to do it for you to be exposed to this previous material in case you haven't seen it. And don't worry about it. I mean, in any case, we're gonna see selection rules briefly again when we go to time-independent perturbation theory. So, well, the second part, which I think it's quite interesting, and uh, usually it's not included as part of this course, but I think it's quite interesting for you to know, is that you can interpret, specifically non-degenerate time-independent perturbation theory as an iterative method. So I'm giving this for completeness because I think this is very interesting and actually quite illuminating in the fact of, well, why do we bother to do this expansion in terms of lambda and at the end making it equal to 1, right? So, I mean, of course, it's a good method. It's nice to keep track of the different orders, but if you make it at the end equal to 1, it would some way make seem the lambda necessary of, or, irrelevant in a way. So again, we use lambda to keep track of the orders. Um, but at the end of the day, in the previous exposure, we just made it equal to 1. Because the case we're interested is basically h naught plus h prime. So what I want to tell you is that up to second order, basically the same energy corrections and corrections to the wave function to first order can be obtained equivalently by formulating our problem as an iterative scheme. So if you are computationally oriented, that's actually quite interesting. And we don't even need to involve the parameter lambda. So, I mean, this might be interesting if you have an affinity with numerics and programming, um, and especially if you like algorithms or algorithmic way of thinking. But in any case, let me present the details. So the problem, and I'm going to use a notation slightly different to what I did last time, but never mind. I mean, I think it will be clear enough. And if there's a difference, I'll try to stress it. Okay. So our problem is that we want to correct the eigenvalue problems for Schrodinger equation with a perturbed Hamiltonian, right? Which differs from the old one that we had. So we will have a new Hamiltonian H, which is H naught, then perturbed part, which is the old Hamiltonian, plus H prime, which is a perturbation. Notice I'm not using the lambda parameter right now. So that's important. Okay, at this point, it's not going to exist. So, okay, this is time independent problem because I'm not assuming time dependence of any of the potentials. And we have to recalculate the stationary states, of course, because if we have a new Hamiltonian, we have new eigenvalues and new eigenvectors in principle. So of course, the stationary states are the spatial part of the Schrödinger equation when we do separation of variables. And for the perturbed problem, which is the old Hamiltonian, so we have for the old Hamiltonian H naught, and then I have my phi n equal to epsilon phi n. So notice this is where I am using the new notation. So I'm using epsilon for the old eigenvalues or the old energies, but never mind. And we want to find the new eigensolutions, right? Of course, so for the new Hamiltonian, we want to find the new eigenstates psi n and with eigenvalue en. So I'm using E for the new eigenvalues. And so, okay, we have to calculate new eigenfunctions, but even the old eigenfunctions were a complete set beforehand, meaning that they could represent any element in the Hilbert space. So even if we have new eigenstates or new eigenfunctions, they can be expressed as a series in terms of the old um, eigenfunctions, right? So we have this expression, this expansion, in terms of all eigenfunctions with this coefficient. And of course, the index n identifies the new eigenfunctions you're interested in obtaining. The index I is the index of the sum. And yeah, the coefficient is having this notation CIN. So that might be also different as opposed to the previous notation we used. In any case, we're going to do part of what we did for non-degenerate perturbation theory, which is, let's plug in this expression, the series solution, right? Of course. So on this part with H, with this formula, we have H psi of n with this sum. So we have this equal to the new energies times psi of n, which is in terms of the old ones. Now, we're going to apply the energy operator. For this part, we have the easy part because, well, the phi's were eigenfunctions of H naught. So they're going to pick up an epsilon n, which is why this appears here. So we simply decompose by linearity in the sum. Then we have the application of H naught to the psi i's, which gives us epsilon i's. And then I have plus the H prime part, and this by linearity. And then this stays the same. Now, we basically project into the state J by taking inner product. So that's an old trick that you might also remember if you take a second look at what we did in the non-degenerate case to get the matrix elements in the perturbed eigenbasis. So I'm going to do that. Then I have this. I mean, this is easy. I have the inner product. Then I have the matrix coefficient for H prime with phi j and phi I. And then again, by linearity, I have this. So we have an orthonormal basis because we have solved this problem previously. And so we can simply substitute for the Kronecker delta ji. So this case and this case is quite simple. This is just a matrix element, of course, in this notation for H prime. And well, we can have two cases, right? Because we were looking basically at the state n. So let's say we choose j equal to n, right? So in that case, this is 1. So uh, basically only the nth term will survive in the sum, which is why you have this. Then you have the sum over I, plugging in j equal to n in this case. And again, only the nth term survives. So let's assume for the moment, or for the case that CNN is not 0, you can simply divide. And so this gives you the new energy in terms of the old energy, this correction, or sorry, this matrix element, H prime n n, and then we divide the sum basically. What we have done here, notice by the way, is that we have split this sum in two parts. One is related to the term n. The other, since we have already taken care of n, is the sum over all elements not equal to n. Okay, so that's why we have this simplification. So we have just simply basically divided by CNN, and that's why we have the sum for all cases not equal to n. And so we have Cin divided by CNN in this case, because we divided by CNN, which is assumed not zero, multiplied by H prime Ni. Now, for the case J not equal to N, basically, well, we'll have the other case in terms of the Dirac deltas, right? So we just have to plug in. And so basically we have Cjn epsilon j plus the sum over all states not equal to n, Cin h prime ji, and then CNN h prime jn. So I have done the same splitting of the sum as the nth term. Uh, so, and then plugging in the j, which is not equal to n, and then all the terms that are not n, right? And then I have this one, where basically I have CJN. So I'm keeping the only term that survives from this delta, right? So that's why I'm getting the J over here. Okay. So far so good. And in this case, it makes sense to gather En with epsilon j because they have the same coefficient. So this assumption of En minus epsilon j comes in handy, which is actually the non-degeneracy assumption that we made before. And if we do that, we simply obtain the formula for the coefficients. Uh, so the sum, basically think of the elements, I gather them, then I divide by this difference in the denominator. And then I have this coefficient equal to the sum over all states I not equal to n of Cin h prime ji divided by En minus epsilon j plus CNN divided by En minus epsilon j h prime jn. So, okay, so far so good, right? I mean, um, my logic is following mathematically in a way. But what I want to do is that I want to formulate non-degenerate time-independent perturbation theory as an iterative scheme. And let's keep the eye on the prize, right? Basically, what we want to find is the new eigenvalues and the new eigenfunctions. Finding the new eigenfunctions is equivalent to find these coefficients Cin that we proposed at the beginning. So um, how are we going to do it? Well, we're going to use an equivalent version of these two formulas. Um, well, actually, two pairs of formulas as a way to define an iterative scheme. And think about it computationally, right? When you write a program and you do an iteration, okay, and let's say you do an iterative scheme. So your new values rely on the old values, but for the uh, first values, you need an initial guess, and you need a good guess. And so you can guess that a good initial guess would actually come from the solution to the perturbed problem. That actually makes a lot of sense even computationally, because let's say that somebody tells you, well, give me a correction to the eigenvalues and eigenfunctions. What is your first guess? Well, I mean, my first guess is like for small perturbations, meaning for h prime small, the eigenvalues and eigenvectors won't be too far away from the old ones. So let's use them, because in any case, the iteration is going to refine them. So that's what we take as initial guess, which is actually a pretty reasonable guess on terms of physics grounds if you assume that the perturbation is small or even computationally, which is actually a consistent condition for the unperturbed case h prime equal to 0. So just to be consistent with the unperturbed case, which means, okay, choose the initial guess for the new eigenvalues as the old eigenvalues, and choose the initial guess for the new coefficients as the old coefficients, right? Because at order 0, the new eigenfunctions are going to be equal to the old eigenfunctions in the case you have no perturbation, or in the limit of h prime going to 0, essentially, right? So this is our initial guess, which is good on physical grounds. And I have introduced a notation where we have this subscript term under parentheses, where k indicates, in principle, in this algorithm, the kth step of the iteration. We're going to make a match later on with the order of the perturbation, but at this point, I'm just describing an algorithm. And so at order 0 in the iteration, this is just the initial guess. Okay. So again, we initialize the values with the best guess we can make at the moment or at the beginning, based on what we know for the problem without any perturbation. And so this is actually equivalent to the consistency condition to the zero ordering perturbation theory. So at least at that level, I'm presenting some matching of the methods. So what about for, well, okay, so here I'm just presenting a simple proof that this is equivalent to the zeroth order perturbation theory. This is equal because essentially h prime is equal to 0 in this level. And so many terms vanish. And on this side, everything vanished by h prime equal to 0, which tells you that uh, the new eigenvalue at order 0, which is the initial guess, is equal to the old eigenvalue. And likewise with the coefficients, where you have a zero equality, where, well, basically, so this is one of the formulas that we had before. These terms vanish because h prime is 0 in the non-perturbative case. Then you'll have the plug-in of delta jn ej. Because j is not equal to n, this is equal to 0. And again, this is also because this coefficient is 0. So, well, we have a well-satisfied consistency condition with the unperturbed case. So now this is where I present the formulas that are going to let us iterate from one uh, step of the iteration to the next one. So which meaning that we advance from the initial guess to the first step to the iteration. Having computed the first step to the iteration, we go to the second, and so on and so on. And so these are equivalent actually to the formulas that we found before. Um, so say for the energy eigenvalues, we put them in terms of the all the coefficients and the initial values for the eigenvalues. And let me um, present you with this. So if you think about it, this is the formula that I had for the energies, right? And remember that usually the corrections to the energies come from, in the non-degenerate case, from taking inner product with the same state that you're taking care of. So that's why you have the case j equal to n in here. So I'm going to use this formula. It's just that I'm going to use it as an iterative scheme. If you notice, so this is advancing the new values for the energy as this formula, but the coefficients are of the previous order, right? So the k plus 1 value is being defined by the kth case. And if you think about k equal to 0 is basically our initial guess. So this is advancing the first step of the iteration, which gives you the first approximation to the eigenvalues in terms of the initial guess for the coefficients. Then I had an equivalent formula over here that I presented before, um, that is going to inspire to get this other one, right? So, okay, this is what matches exactly by taking inner products with j not equal to n. But okay, let me define an iteration inspired by this formula, where I define the new value of this coefficient in terms of the old values of the coefficients and the old values of the energies. So now it's clear how I'm advancing from the kth step to the k plus 1 step, okay? And again, think about the case k equal to 0, right? So this would be the old values for the energies and the old values for the coefficients, and this would be giving me the first step approximation beyond the initial guess, where j is not equal to n, of course. And notice that I'm using the assumption of non-degeneracy because I take this denominator, so that's important. In fact, also notice that here this coefficient is not 0 at the beginning because I assume that at first order I have a Kronecker delta. So this would be, for say, the case k equal to 0, 1. So I have no issue there. The third condition is simply inspired from the normalization condition. So, I mean, the new value of the coefficient CNN at the step k plus 1 is basically the inverse of 1 plus this, well, the sum of these ratios. Where does that come from? You might have an eye for that, but basically the last rule for the square norm of the coefficient at the step k plus 1 is an iteration inspired from the normalization condition because, okay, I know that the norm of the state has to be 1, which is, this is some sort of Fourier theorem. So, which is basically the sum of the coefficients squared, so the norm squared, of course. And I simply do some splitting between the case I equal to n and the case I not equal to n. If later divide all this formula by CNN squared, I get that the inverse of CNN squared is 1 plus the sum over all states not equal to n of this ratio. And so this is, I mean, this is something that holds exactly. This is approximate in the sense that the new values of the iteration are defined in terms of the old ones, inspired by this formula. I'm not relating the order k with the order k. Uh, I'm relating the k plus 1 step with the kth values. So it's inspired from this. This is kind of saying you that the normalization is happening approximately, not exactly, but approximately up to the order that you are performing. Because later I will show the equivalence with perturbation theory. And so, okay, this is basically, I'm giving you some rules and then telling you, well, check what you get for basically k equal to 1 and k equal to 2 for the energies, which is first and second order corrections. Um, and well, k plus 1 equal to 1 and 2, and then k equal to 1, or sorry, k equal to 0 for the wave function coefficients. Okay, so I'm just going to show that we get the same formulas that we got for time-independent perturbation theory. First of all, as an iterative scheme. Second of all, as without invoking the parameter lambda at any point. So I think this is quite interesting, both for computationally oriented thinking and also to get to the fine details of the method. So, okay, we'll see how the iteration scheme will let us obtain the same corrections that we presented for non-degenerate perturbation theory. So let's advance from the zeroth step, which is the initial guess, to the first step, right? So I'm going to use exactly these formulas. So let me plug in, right? So k is equal to 0, basically. So that's why I have k plus 1 equal to 1. So this part is known, this part is known. Then I have Cin, this is a sum over I not equal to n. So this value, remember the initial guess that we had for the coefficients, right? So this was 1 and the others were 0 because I is not equal to n and I had the Kronecker deltas. So this is going to vanish for all these terms. And I just have the old energies plus the matrix element h prime and n. So think about it for a second. The second part is basically, okay, I take k equal to 0, so Cjn1 is equal to this sum of Cin0, where I is not equal to n. So clearly these terms are going to vanish. Now I have the non-degenerate case, so I mean, this is not vanishing. So I don't have an issue in the denominator. And then I have h prime ji. So this vanishes altogether. And then I have basically this other element. So C and n to order 0, which was equal to 1, again by assumption of these Kronecker deltas for the coefficients. And then n 0 and plugging k equal to 0 minus E0j. So again, notice that the non-degenerate assumption of basically having degenerate spaces for the energies is quite important even in this case. So this term is going to vanish. This is equal to 1. Then I have h prime jn, and then I have, well, also remember that the assumption at order 0, or say the initial guess for the energies, is that they were equal to the unperturbed energy. So that's why I'm going to have epsilon n for this value. So I have this. And so you start to recognize some terms, right? So having plugged in the initial guess value for the energies, I have this formula. Then I have the normalization condition, right? And so I have k equal to 0, which means that I have CNN 1, then 1 plus, and again, I have basically states that are not equal to n, and then I have C1n in the initial guess. So this is 0 together. So because this is 0, this is 1, 0 over 1, 0, 1 plus sum over 0, so I have 1. And this was actually the value of C0 and n squared, if you remember, by assumption, because it was this Kronecker delta, and I'm the case I equal to n. So I mean, the simplest case in this assumption is saying, well, actually it simply takes C1 and n as C0 and n, which was 1, right? So this was a condition from the norms. So I guess this is defining things up to a phase, but it kind of makes sense because this is the only term surviving in a way that you just take the same value. And this is nice because, first of all, well, to first order, or the first step approximation to the coefficients, gives you the first step approximation to the new eigenstate. And so this is a series representation. And I can do the same splitting as, okay, the state n and all the states not equal to n. So for this coefficient, I know that the value is 1. Then I have all the states not equal to n, and I look for their coefficients obtained by this formula, and I plug in this formula. And so this is quite nice because, okay, at this point, we're just on first order. But look at what we got for the energies in the first step of the iteration. This is telling you that the approximation at the first step for the energies minus the old values for the energy, which was the zeroth step approximation, is basically H prime NN, which is the matrix element of H prime in the unperturbed basis states phi n, which is exactly what first order perturbation theory predicts. So at this point, at first order, this formula in the iterative scheme coincides with first order perturbation theory in the non-degenerate case. Likewise, for the formulas for the coefficients, basically the matrix element divided by this, where we are assuming that we have non-degenerate energies, etc., etc. This is also the first order correction that we got for the wave function coefficients. And this is also the first order correction just by, I mean, implication of the first order approximation to the wave function state, right? So the unperturbed part plus basically the perturbation, adding components in a states not equal to the original, and this is the correction term under this state. So we have gotten the eigenvalues, eigenfunction coefficients, and therefore eigenfunctions of the first order with this iterative scheme formula exactly equal as the first order perturbation theory. In the non-degenerate case, of course. So we have this coincidence of our method, which is iterative, with the theory that we presented before. Now let's go to the iteration for the eigenvalues at the second step, right? So that means k equal to 1, so that k plus 1 is equal to 2. And so if I were to go over this formula, because I mean, I just care about the second order for the energies. So this remains the same. It's just now I have to use the k equal to 1 for these coefficients, right? And so we go to this formula. So this stays the same. Notice that actually this is the first order approximation. So that's interesting and for you to think. And so then we have the sum of our states not equal to n of these coefficients in the step 1. So this didn't change because this was, well, the CNN the first step was equal to 1. This one's changed, so we'll have to use this one. But notice, okay, that they're multiplied by h prime and I, right? So that's the way we define our iteration formulas. And invoke, well, this is 1, so we're not going to write it anymore. And invoke the formula that we got for the coefficients to the first step. So I have to plug in. So CIN was H prime IN divided by EN minus EI. And then this was multiplied by H prime and I. So this is actually interesting because one is the conjugate of each other. And so I have these two terms which haven't changed, and then I have the norm squared of this matrix element, and then divided by the energy difference over all states not equal to n in non-degenerate perturbation theory. So this is actually also coinciding with perturbation theory non-degenerate to second order, because I'm taking now the difference between the the second step approximation to the energy minus the first step approximation to the energy in our iterative scheme, which is basically our some sort of second order correction. So I take the difference. Now it's evident that this is the second order correction, uh, because, okay, this would be the first order uh, approximation to the energies in perturbation theory. This is the first order correction. So the difference with all this is the second order correction. And now is the sum for I not equal to n of the matrix element squared divided by the energy difference, which is not zero in the denominator because we have the non-degenerate case. And this is exactly also the second order correction found with perturbation theory if you compare with the formulas that you saw last time in the lecture. So, I mean, of course, in principle, because it's an iterative scheme, we could go on and on with higher values of k, etc. But I mean, if we were to do it, let's say for the wave function, which is usually not done, but this would be quadratic in terms of, or quadratic powers of h prime ji. So, I mean, up to the orders that we explored in the previous lectures for the non-degenerate case, we have shown that our iterative scheme is completely equivalent to first order corrections to the wave function and second and first order corrections to the energies eigenvalues. So, so far we have showed equivalence, which I think is quite interesting. And also I want to stress without using the parameter lambda equal to 1. So that's one thing. Uh, in a way, this is partly showing the redundancy of the lambda parameter. On the other, this is why I made the comment that if we were to do the iteration to for the wave function coefficients to second order, it would be quadratic, because now the order is related to the matrix elements rather than the lambda parameter. I mean, it's nice if you multiply the lambda by the matrix perturbation, the lambda will keep track of the order, but I mean, you can also think of the powers as keeping track of that order. So again, this iterative scheme is equivalent to a perturbation method in terms of powers of the matrix elements, h prime ji. And you just have to compare the degrees of the powers appearing in the approximation to eigenvalues and wave function coefficients, except for this one. I mean, this has its own formula, right? Because it's kind of weirder with the normalization. But I want to comment one last thing, which is, okay, again, I'm emphasizing the iterative scheme presented is equivalent up to second degree to non-degenerate time in the perturbation theory, at least for the energy eigenvalues. And we haven't proved it, but look, perturbation theory or perturbation methods mm, have some concepts that are beyond the scope of the course at this point, but when you do a perturbative expansion, it's understood as asymptotic. And the fact that it's asymptotic is a tricky concept to explain. Again, it's beyond the course and is usually, I guess you could say, grad school level. But the way I'm going to short or briefly explain asymptotic is that the accuracy is related to a small size of the perturbation rather than making the order go to infinity. So I want you now, okay, we present the iterative scheme as not being related to lambda at all. But imagine that instead of, well, we started with this perturbation, right? So imagine that I introduce the lambda over here. So actually my whole perturbation will be lambda h prime. And the same way that I was thinking of in this iterative scheme that the perturbation is according to the powers of the matrix element, in that case, it would be the powers of the matrix element lambda h prime j. And so that's the explanation of why adding the lambda parameter keeps track of the order, right? Because in this case, it would be a factor of the H prime matrix, and therefore the powers of the matrix coefficient will show powers of the lambda parameter. So you can think in both ways equivalent. I mean, one of them, uh, somehow you can do the perturbative approach with or without the lambda, keeping in mind that the perturbation has to be small. When you have the lambda parameter, you can define the small in two different fashions, either making h prime very small or making lambda very small, like in the limit lambda going to 0. If you don't have a lambda in your perturbative expansion, you also have to define that the perturbation is small, and that means defining matrix coefficient h prime being small enough. Remember the problem where we had to recover the whole basically Taylor series, and we needed a condition for this two-dimensional problem, general two-dimensional problem, where we had a condition that the potential divided by the energy differences in when taking the norm had to be equal to 1/2. So that's a condition of the perturbation being small compared to the energy differences. Okay, so that's a problem that I did 2 lectures ago. But again, where we have the perturbation multiplied by a lambda parameter, um, so what is critical for these approximations to be well behaved and to make sense when you compute them, which is stressed by that problem that I did 2 lectures ago, is precisely that the perturbation is small. And well, what is the perturbation parameter to be small? So either lambda goes to 0 in the limit or small matrix coefficients. If you have the lambda multiplying h prime, then that means that the product lambda h prime has to be small by itself. And these are two different avenues under which you can attain that, right? Let's say you fix the value of lambda as equal to 1, then this one has to be small. Let's say that you have a fixed perturbation, h prime, that is in principle not small. You have to make lambda small by going to the limit. So that's where the perturbations make sense, because otherwise you might have a divergent series, as the problem of 2 lectures ago for a general two-dimensional system showed. So, and I think the iterative formulation is helping to clarify that by the fact that it doesn't need a parameter lambda. And then you notice that the perturbation is in terms or in order of the matrix coefficients. And then you go back to introducing lambda, and then, okay, you understand. And so it's important, or just what I want to emphasize is that in asymptotic expansions, it is more important that the perturbation is small rather than the order of the perturbation going to infinity, right? So that's why we decided to stop at second order, because it's way more important to be careful that the perturbation is small. With respect to what? Actually, with respect to the energy difference, as a necessary but not sufficient condition, rather than going to say third order, fourth order, k going to infinity in either the order of perturbation theory or the step of the iteration, right? So it's more crucial to have a small perturbation, meaning either lambda going to 0 or lambda small enough, or the matrix coefficient small enough, or matrix coefficient small enough, rather than making the order of the iteration or the order of the step of the order of perturbation theory going to infinity. So that's why we are allowed to basically stop at a small order, like k equal to 2, which is second order for the energies. And again, understanding that in order for the method to be a good approximation, there's a necessary condition. It's not sufficient, it's necessary, which is essentially the conclusion of the problem that we did 2 lectures ago, that the perturbation in this product, now I introduce again the parameter lambda. So the perturbation, which is lambda times matrix coefficient, has to be considerably small with respect to the energy differences En minus Ej. And well, I mean, if you want, actually, it will be much more clarifying to write this in norm, because you can have the cases of plus and minus, right? So there's a symbol for this, but I'm going to leave it like this for a moment. So that means that the perturbation, when you introduce the parameter lambda, it has this form. If you make lambda equal to 1, of course, this goes away, but that means that the perturbation has to be small with respect to the energy differences. And so this was, again, the same conclusion we found in a problem 2 lectures ago for the general two-dimensional system. And again, also, I want to stress that this condition is necessary, but it's not sufficient. This is a very, very simple condition that does not guarantee that you will have a good approximation. So you have to be careful on the perturbation being small. If you want to know more about this, I encourage you to check Saxon's book. So I have listed some references, of course, what I have used to, what I have consulted to prepare the lectures so far in time-independent perturbation theory, um, so that you guarantee good convergence. So again, the perturbation has to be small, meaning that either this parameter is small, or this matrix coefficient, or the matrix coefficients are small with respect to their respective energy differences. There is a stronger condition, which is, I don't think it's sufficient either, but it's stronger and it calculates the standard deviation of the matrix element related to H prime. So, but that you'll have to check more. I mean, it's beyond the scope of the course. I'm just trying to present the spirit, and the spirit is that it's more important to have small perturbation than to go to higher orders in perturbation theory. And that's why we stop at second order in the energies and at first order in the wave function or its coefficients. So just keep in mind this. This is actually quite reasonable. You have some experience from the previous problem in lectures ago. If I basically pass dividing, this is what we got. So, okay, I hope this clarifies a little bit that this alternative presentation of the method as an iterative scheme, where I'm not using the lambda, illustrates that the formulation can be done without uh, introducing a parameter lambda. Introducing it is convenient, of course, to keep track of the orders of the perturbations. Also, because, I mean, you cannot determine beforehand the size of the perturbation matrix, right? But you need the conditions of small perturbations, and the lambda can help you in this limit to basically satisfy that condition of small perturbations with respect to energy differences. In the case that you enforce lambda equal to 1, as we did in the first presentation at the very end of perturbation theory, well, then just keep in mind that the perturbation will give, or perturbation theory will give good results provided this h prime j n is small enough compared to the energy differences. So I hope you like the topic. I know this is a new method and perhaps a new way of thinking, but it's important to be aware of the physics and on the mathematics. And also in this case, I have tried to present an alternative computational approach, which is equivalent to the mathematical method. So if you want to know more, of course, I mean, my sources for consultation in terms of preparation of this class have been the Griffith's book, the McIntyre, another mathematical book in terms of perturbations by Holmes, the book of quantum mechanics by Saxon, and my own notes as when I was a student like you in physics. So hope this was clarifying, and I will be posting the homework of time-independent perturbation theory very soon. So see you soon.